Okay, here we're going to be trying to sketch the graph of f of x equals ln of x squared plus 1. Okay, so y equals ln of x would look like this. This is an asymptote here, and right there would be when x is 1. When you do the natural log of 1, you get 0. Okay. And so your outputs can be negative. They're negative when you're right in that area. They can be positive. So the outputs go from negative to positive infinity in general. But notice how the inputs can't be 0 and can't be 0. That's the issue with the domain. So when you're doing the domain on this one, this x squared plus 1 has to be greater than, it can't even be equal to, has to be greater than 0. Okay. Well, it's going to be, because think about it. If you subtract 1, x squared would have to be greater than -1, and x squared is always greater than or equal to 0. So it's going to be greater than or equal to -1. Okay. So this one right here is kind of interesting because the domain, there are no domain restrictions. So you can plug anything from negative to positive infinity in there for x, because when you square it, it'll be positive. Add 1, it's going to be positive, and you can do the natural log of a positive number. Okay. All right, the other interesting thing here you might want to keep in mind is on symmetry. We've seen this a couple times. Notice how if you plug in a negative x for x, you're going to be squaring in there and then adding 1. And so you're going to wind up getting the same thing, because when you square, it'll become positive. And so that does equal f of x. So just keep in mind, we're going to have y-axis symmetry. So whatever's on the left side is going to match whatever's on the right side of the y-axis. Okay, so that helps us just double check things. Okay. All right, after we do symmetry, we'll consider the first and second derivatives. In the first derivative, we wound up doing 1 over, and it was supposed to be absolute value of x squared plus 1. And then we do the chain rule on the inside, so we multiply by 2x. But you don't really need those absolute value when you think about it, because this is always positive anyway. So you don't really need them. They're not adding any more to it. So the easiest thing would just be to write it as 2x over x squared plus 1. Okay, so that's f prime of x. All right, now f double prime, I won't go through the whole process. We did that in another video. It's quite a bit more complicated. I'm going to write it in factored form. It was -2 times the quantity x squared minus 1 over x squared plus 1. And really, I could factor the numerator, but I like this works out good when I'm trying to test positives and negatives, so I'll leave it there. Okay. All right, so those are the derivatives. So now we're looking for where is f prime of x equal to 0 or undefined. And then we want to know the same about double prime. Okay. All right, so when you're looking at where is f prime of x equal to 0, if you look over here, for a fraction to equal 0, the numerator would have to equal 0. And that happens when x equals 0, and there's nothing making it undefined, because you can plug in positive, negative, or 0, and you won't get a 0 in the denominator. Okay. And then undefined, again, it's not going to be undefined, because it would be where does that equal 0, and it would be nowhere. Can't happen. Okay, so you don't get any places where it's undefined. All right, same thing here. X squared plus 1 is always going to be positive. You can square that. You're not going to get a 0 in the denominator. And then to find out where f double prime equals 0, you set the top equal to 0. All right, so I will go ahead and factor this further, or I could have used square root property. And then I get a solution from here, and I get a solution from here. So x could equal 1. Let me not go so far down so that I have more space. I want it kind of closely lined up. So x equals 1, x equals -1, And then you don't get anything from there because there's not a variable with it. -2 could equal 0, but that doesn't give us a solution, give us an answer to that. Okay, so possible inflection points are going to happen at 1 and -1. The possible max or min is going to happen at 0. Okay. All right. Now, when you're to the left of 0, so this is the point I'm checking. When I'm over here to the left and over here to the right, if I were, let's look up here, the denominator, notice, is always positive. So when x is negative, I'm going to have a negative on top divided by a positive. And when x is positive, the numerator will be positive. The denominator always is. Okay, so that means it's going to be decreasing followed by increasing. Okay, which makes that point 0 something, makes that see, that's decreasing, increasing. So it makes it a minimum, doesn't it? Value. All right, so let's go ahead and find out where, what the y coordinate would be. And let me just remind you that f of x was natural log of x squared plus 1. So if you plug in 0, you're going to get natural log of 1, and natural log of 1 is 0. Okay, so 0, 0 is going to be a minimum. All right, now let's consider the inflection points over here. Okay, let's go ahead and put 0 on this also. We'll just break it up a little bit more than we normally do. Okay, so if you're over here, these are the possible inflection points. Okay, and if you're over here at, say, -2, we're checking in f double prime to see what the sign would be when you plug in a -2. Okay, so that would be, this would be 4 minus 1. 4 minus 1 would be 3. Okay, I really don't even care that it's 3, it's that it's positive. And then that times -2 would be negative on top. And this down here is always positive, isn't it? Because you're squaring, adding 1, and then squaring again. So when you're over here at -2, you're going to wind up with a negative. Okay. All right. When you're in between -1 and 1, plug in, say, a 0. Do you see on top, we're going to get a -2 times -1. We're going to get a positive, and the denominator is always positive. Now look, that's true. Like if I plugged in a -1/2, so I broke it up a little bit more in a +1/2. See, it's right in between those two has to be the same thing because there's no other possible inflection point. So you don't really have to test both of them, but I want you to think about it that way because of the first derivative giving us that this was an important point. Okay, so anyway, if I did put in a half, then that would be a fourth. So I'd get a negative times a negative is a positive over a positive. Put in a +1/2, I'd get the same thing. Okay, so that's basically this interval, it's positive. And then when you're past 1, you put in a 2, then you're going to get a positive for that x squared minus 1, but then that's negative. So this will be negative again here. Okay. All right, so that's concave down. So from like -infinity to -1, it's concave down. From -1 to 1, it's concave up. And then from 1 to positive infinity, it's concave down again. All right. So right underneath there, I'm going to do the graph. So let's put our minimum. Okay. And that turns out to be both an x-intercept and a y-intercept. Okay. We don't need a whole lot below because we know this is going to wind up having everything be above. Well, do we know that? I know that. Okay, let me just put the minimum value is 0, 0. So we know there's nothing below that. Then we're going to come over here at -1 and at 1 and see the change down to up to down. Okay. So that means those are going to be inflection points here and here are inflection points. Okay. All right. So that's going to be a minimum. All right, let's find the coordinates of the inflection points. Okay, so this is going to be down, up, down. Okay, so this is going to wind up being an inflection point at -1 something and at 1 something. Let's plug it into the f function, which is over here. When you plug in -1 and square it, you get 1. So this will be the natural log of 2. And the natural log of 2, find my ln button of 2, that turns out to be about 0.69. I'll just say 0.7. Okay. And then there is x-axis symmetry. So when we get over here, should get the same thing. And you see why? Because when you plug in a positive one, you still get ln of 2. And that's going to be about 0.7. Okay. So we'll be, move this down a little bit. Give myself just a little bit more room. So let's make that 1. Let's make this 1 and this -1. All right, so 0, 0 is going to be a minimum. At 1 and 0.7, a little less than 3/4 of the way, and at -1.7, you're going to have inflection points. In between -1 and 1, it's got to be concave up. So let me get that in there. And then after 1, it's concave down, and after -1 to -infinity, it's concave down. So I guess it's doing something like this. Okay. All right, so let me now not be so sure. I don't know if it's flattening like that. Okay. So let me think about asymptotes. Regular ln functions don't, like that. When it does this, it's not a horizontal asymptote. It continues to increase. So I don't think this is going to have an asymptote. No, because as you let the natural log of something getting bigger and bigger and bigger looks like this and keeps going. It doesn't approach like an asymptote of any kind. So that's what you get, something that looked like that. Okay. I'm gonna, yeah, nice, pretty. All right, I like to graph them after I'm done and see how it wound up looking. And that looks real interesting. Okay. All right, so that was example 7, which was a natural log function. All right, so if you haven't yet, you want to get started on homework.